It's my pleasure to introduce Kristen. She is the director of, as you can see on the screen, Economics for Equity and Environment Network, otherwise known as the E3 network. I've been affiliated with them for 2 or 3 years now, and it's just exactly what academics generally and economists specifically should do, to be engaged in public policy, to help ask the tough questions, to provide answers that sometimes are necessary in the public discourse. And Kristen has led it beautifully in the last few years. Prior to being the head of the E3 network, she was an associate professor at St. Mary's College in Maryland, right? So we welcome Kristen to this series.
Hello. So I understand that you all heard from Bill McKibben and some of the members of his 350 team recently, okay? And so obviously he was talking about the imperative of getting CO2 emissions in the atmosphere down below 350 parts per million. What I'm going to talk about today is sort of the economist's take on that in terms of, what's it actually going to take, what steps are we going to have to take to get there, and most importantly, is it affordable? Is this economically feasible at this point in time? I remember a conversation with Bill sometime roughly around this time, maybe last year, as he was gearing up for his big 350 push in fall of '09, and told him about this initiative that E3 Network had put together to kind of explore the economics of 350. And I remember he had sort of kind of a tentative voice on the phone, sort of, well, what are you going to say? I said, well, it's not finished yet, but I think it's going to look very promising in terms of being able to get a lot of economists to come out in favor of the economics of 350. But he had right to be cautious because a lot of economics up until fairly recently has not been supportive of even emissions reductions goals that are far less ambitious than 350, and that's one of the things we'll talk about today. But first, a little bit about me in the E3 network by way of helping to sort of frame where I'm coming from in this discussion, and also to give you a sense of the many people upon whose shoulders I'm standing in kind of doing this presentation today. E3 is a national network of economists. There's more than 200 of us now across the country. We've been around for about 3 years. And we're economists who are dedicated to doing applied research in support of environmental protection. What defines the research of E3 economists as, say, distinct from other economists is a very firm commitment to social equity. We see social equity evident in the questions we ask and the methods that we use to go about answering those questions. And then within the larger network of 200 economists, we have a smaller group of about 25 economists, and John is a member of this group. We call it our Climate Task Force. And this group is engaged specifically at looking at what are the important policy-oriented questions that need to be answered with respect to moving climate policy forward in the U.S. And it's that task force research that I'll be focusing on a lot today. One thing I want to mention, though, especially for graduate students who may be here in the audience, we do a lot, E3 Network does a lot of programming for graduate students, because one of the things we want to do is create a pipeline of new economists who can go out and work actively for environmental protection, engage in public policy discourse. And so we have an internship program. We have, every other year, we have a graduate student workshop where we bring together 20 graduate students and about a team of economists from across the country to kind of share ideas, promote research around theses and doctoral research. So if you're a graduate student in the audience, I encourage you to take a look at our website, www.e3network.org, and see if there's a program there that isn't just right for you. And in the past, we've considered applications and participation by advanced undergrads, including those who already have sort of firm plans in place to pursue some kind of graduate education in economics or a related field. So just wanted to kind of give that plug for all of you. Okay. One example of the kind of research that E3 Network helps to support and promote and bring into existence is this report here that I'll be talking a lot about today, called The Economics of 350, The Benefits and Costs of Climate Stabilization. And this is authored by 8 economists in the E3 Network, most notably the 2 lead economists, Frank Ackerman and Elizabeth Stanton, who are at the Stockholm Environment Institute here in Boston. But there are 6 others, including myself. And for those of you who know a little bit about economics, finding 8 economists to agree to anything is a feat in and of itself. So we're particularly proud of this piece of work because it's very ambitious in its goals. And to get 8 economists who say, all right, is really an accomplishment. Okay. what I want to do first today is kind of take a step back and think about, you know, what are the objectives for climate policy, right? Where are economists jumping into this discussion? And of course, the objective, as many of you are probably all aware at this point in time, is we're aiming to keep warming within 2 degrees Celsius change from 1990. Right? That's the amount of warming that has been identified that we can tolerate without suffering undue risks of some of the worst harms from climate change. And as of 2007, there was more or less scientific consensus recommending a 450 parts per million CO2 stabilization level. Okay? That is, if we stayed within 450 parts per million, right, we could maintain warming at 2 degrees Celsius or less. To get to 450 parts per million, we understood that we needed to reduce emissions by roughly 80% of 1990 levels by 2050, right? No small undertaking. And the good news, right, because it's always important to find some good news somewhere in all of this, is that slowly but surely we're seeing climate policy in the US and abroad slowly inching forward towards that 450 parts per million goal, right? That's the goal that's implicit, for example, in the suite of proposals that are under discussion right now in the US Congress. The bad news, however, oops, is that 450, it turns out, is so 2007. Climate science, unfortunately, is moving a lot faster than policy. All right? And as you heard already in some of your previous discussions as part of this series, there's more and more evidence of potential harm at lower temperatures and lower CO2 concentrations. James Hansen has warned that a doubling of CO2 in the atmosphere is likely to cause 6 degrees Celsius of warming, not 3 degrees Celsius, as was previously believed. All right? So the climate is far more sensitive to increases in CO2. Hansen has also warned that 450 parts per million may indeed be the threshold for an ice-free Earth, in which we will see disastrously higher sea levels, disruption of global water supplies, and some of the other more catastrophic events that are associated with climate change. Right? So 450 may not be good enough. And this is coalescing around a new recommendation to get below 350 parts per million as quickly as possible. And so what was seemingly a Herculean task of getting to 450 parts per million now is a seemingly impossible task of getting to 350 parts per million. And so I think a reasonable question for people to be asking at this point in time is this game over? Okay. Well, it's not game over, but at a minimum, we're going to need a change in attitudes about what's possible, right? I borrowed this cartoon from a colleague who's excellent at culling the best from the newspapers. And this is the auto industry, of course, balking at even kind of a small increase in fuel efficiency standards, saying, what, you expect me to get up that? Right? Well, we're going to have to think a lot more broadly and open-mindedly if we're going to get there. But more seriously, and yet with another cartoon, we have good reason to despair at the change in targets from 450 down to 350. For those who have followed the maddeningly slow pace of negotiations over climate policy, both abroad and here in the United States, you know that it sort of takes this form. In case of global warming, first, make sure everyone in the building agrees there is a fire. 2, bring in a few outside skeptics. Let them talk a long while. 3, consider that it may just be a small fire. 4, realizing that calling the fire department isn't free, you know. 5, lift the hammer. 6, now replace the hammer and repeat steps 1 through 4 again. 7, lift the hammer. And 8, pause to think about who's going to clean up all of the broken glass. And that certainly is sort of where we've been with all of this. What I want to talk about today, though, is that to get to 350, right, is going to require a new game plan, and a new game plan that's rooted in better economics. Okay? In order to demonstrate that 350 is economically feasible, right, we're going to have to adopt better ways of thinking about the economics of climate change. There is no insoluble barrier to 350 or 450, although sometimes economics has led us to think that there are such barriers. Okay? And I'll give you kind of 2 very commonly cited quotes from conventional economics modeling on climate change. One refers to the work of Yale's William Nordhaus and his famous DICE model, which is probably one of the most widely known and widely cited climate economic models, certainly within the academic literature, right? And even as of 2007, what he's arguing is that the economically optimal economic policy with regards to climate change should only involve very modest short-term emissions reductions, okay? Specifically, he says the optimal rate of emissions reduction should be about 14% in 2015, 25% by 2050, and only 43% by 2100, okay? That's a far cry from the 80% reductions that we know we need to get to 450, never mind, as we'll see in a minute, what will be required to get to 350. A second famous quote by Richard Toll, who's also an economist, and is quoted very often by our favorite environmental skepticist, Bjorn Lomborg. He says we should tax CO2 emissions at the economically correct or efficient level of about $2 per ton. Well, if we did that, that would have the effect of raising the price of gasoline by a couple of pennies at most, okay? It's not going to change anything, and it's certainly not going to get us anywhere near the types of emissions reductions that scientists are recommending. And yet here are two very prominent economists, right, publishing in the scholarly literature, claiming that this is what economics says is necessary vis-a-vis climate change. And we can see there's this amazing disconnect between what economics is saying and what science is saying, right? And it's because of that disconnect, well known to those who are active in the climate policy debates, that I think was behind that initial skepticism that I heard expressed by Bill McKibben about a year ago, as I was mentioning. And it's rightfully so, okay? If we take a look at what economists have said more recently about the cost of the proposals that are on the table here in the US. So this would include the Waxman-Markey bill and also the Cantwell-Collins bill that has recently come out of Maria Cantwell, Senator of Washington State. Okay? We see two very divergent views about what these types of policies will mean for the US economy. And I don't mean to treat them equivalently. There are important distinctions between those two bills. But in terms of how economists look at their net impacts on the economy, the effects are almost the same, particularly over the long term. On the one hand, we have economic studies coming out of the U.S. Chamber of Commerce, the National Association of Manufacturers. And they're running around the country, literally holding press conferences in major U.S. cities, okay, where they invite governors, judges, influential lawmakers, media. And they're, of course, proclaiming that, if any of these proposed climate bills in the U.S. were to go through, that we would face enormous prohibitive costs, okay? How do they arrive at these conclusions? Well, it's not altogether that clear, and that's partly because they're basing their research on proprietary models. So these are models that are not published. They are not publicly shared so that other researchers could kind of play with them and sort of see what it is that makes them tick. There's biased assumptions. They assume things like, real market rigidity, no innovation. They assume that, the absolute worst in terms of climate policy design, no technological innovation. It's not that surprising then that they arrive at these conclusions. But the important thing to know is that outside of the U.S. Chamber of Commerce and the National Association of Manufacturers and a couple of other prominent industry-sponsored studies, nobody else is finding cost estimates remotely like these, okay? If we were to look at some recent studies by the Energy Information Administration, the Research Triangle down at Duke, MIT, the Department of Energy, as well as research by other major research institutes and independent economists, what we would find is sort of more or less agreement that the climate policy proposals on the table here in the US will involve low short-term costs and negligible long-term impacts on both job growth and GDP. And essentially what they're all saying is, folks, come on, let's not get worried about the proposals that are on the table here, because all of these proposals we know are too small to solve the climate problem, and therefore they're also too small to really hurt the economy either. Okay. Now, I just wanted to kind of show this graph here quickly, and I'll explain what it means. You know, one of the things that we've been really bad at in terms of thinking about the economics of climate change, particularly here in the US, is learning from the best examples of what we have around us in our own backyard. And so this graph shows per capita CO2 emissions by all 50 US states, right, as of 2004. And it's broken up into the red represents emissions coming from industry and commerce, and the blue represents emissions from transportation and residential use. Okay? And what you can see at first glance is obviously there's a huge disparity in CO2 emissions per capita across the 50 US states, right? When we talk about the effects of climate change and the effects of climate policy on US states, it's really important we talk about, well, what states are we looking at? Where, you know, what states have CO2 emissions that will be affected? But the point I want to draw out here is if we just pull out kind of two states here, California and Texas, the two that are circled, you see that per capita emissions in California are 40% as high in California as in Texas. And yet, Texas and California have roughly the same standard of living, right? Okay. So it's possible to have a US lifestyle, right, in both Texas and California, and yet if you live in California, you could do it with 40% of the per capita emissions of what you would produce in Texas, okay? Now, what does all this mean? Well, you know, first and foremost, in thinking about solving the climate problem, we should be looking in our own backyards. If we could get all US states to match the emissions of California on a per capita basis, we would be talking about an 8% reduction in global emissions. 8%. We could reduce global emissions by 8% if every state in the US could achieve the per capita emissions of California. Now, alternatively, the flip side of that is if every US state were to achieve the per capita emissions of Texas, we would increase global emissions by 7%. Okay? So there are a lot of lessons to be learned just right here in our backyard, and obviously it's a first place to start. Okay. Now, before jumping into the economics of 350 per se, I want to say a few words about why it is that historically, you know, economists have not been on the so-called right side of the climate policy debate, why it is that economic models were consistently reaching conclusions that were sort of seemingly at odds with what climate scientists were telling us, okay? And economic models, like all models, are assumption-driven, right? You change the assumptions, you change the results, okay? And, you know, the economists in E3 Network, as well as others, have been looking at these climate models for a long time now, and there are a variety of them. But what you begin to see are there are a few key assumptions common to all of these climate economic models that really help drive the results that show that we should do only a little bit in the here and now to reduce emissions, right? And that we certainly don't need to be striving for the, you know, major 80% reductions by 2050 in the short term. At least that's what models up until very recently were saying. So what were these key assumptions? The first was, in almost all of these models, you're going to find what's called a high discount rate. And what a high discount rate is if we assume that $1 today is worth more than the same dollar at some point in the future, the discount rate is basically the weight that tells us how much less that dollar in the future is worth as compared to that dollar today. So the higher the discount rate, the less important things in the future are compared to the present, okay? So when we put a high discount rate in these models, then all of the benefits to future generations of avoiding global warming and catastrophic climate changes essentially disappear from the analysis. So that we're talking about paying to reduce emissions in the present, but the future benefits are more or less disappeared from the model because of those high discount rates. A second key assumption has to do with how they model technology and the cost of emissions reduction. What you find is that they'll assume first minimal capacity for energy efficiency improvements, okay? Despite all of the wonderful research coming out of places like the McKinsey Institute and the American Council for an Energy Efficient Economy, which clearly demonstrate a whole suite of energy efficient initiatives that are already proven to be cost effective, that are here, right, available to us, that if widely adapted could reduce emissions by as much as 1/3 in the US, right? These models assume that there's virtually no potential for energy efficiency or other low-cost or no-cost emissions reductions, okay? And partly that's a bias on the part of economic modelers, right? Because what they can't understand is if there's all this potential for energy efficiency improvement, right? If there are all these dollars on the sidewalk and people are walking by and not picking them up, well, that wouldn't be rational, right? So if there is energy efficiency potential, we should be adopting it, right? But of course, that ignores kind of the barriers to adoption that are well known to exist. So these models assume minimal low-cost or no-cost energy efficiency improvements, and they also tend to assume a very slow pace of technological change, as if technological change isn't influenced by public policy, which we know it is, and I'll talk a lot about that toward the end of my presentation. But if you just assume that technology sort of changes, you know, kind of goes along at the same constant pace year after year, then sure, it's going to take a long time before some of the major technological changes we need to make the massive emissions reductions that are required to get to 450 or 350 before they come online. But if we assume public policy can sort of speed up that process of innovation, then we get much lower costs. Right? And then the other thing that they will typically assume are some, you know, sort of dubious near-term benefits from global warming. And two of the favorites that I love, and I credit my colleague Frank Ackerman for always pointing these out. He has a wonderful knack for picking out the absurd features of life that, and these are two of them. One is that in one of the more famous models, again by William Nordhaus and his DICE model, he assumes that the optimal US temperature, that is the temperature that would maximize human welfare or human well-being for the majority of the US population, is an average temperature that's closer to what is experienced in Houston or New Orleans. Okay, and I mean no disrespect to those cities, but they're not places I like to frequent, you know, in July and August when it's, you know, in the high 90s and 100% humidity. And so to say that that's the optimal temperature for, you know, all parts of the US, I think is debatable. And of course, a lot of these models, particularly earlier on, assume that, particularly here in the US, that there would be agricultural benefits from both a longer growing season and the fertilizing effect of having higher CO2 in the atmosphere. And while, you know, the net impact on agriculture is still being debated, more and more evidence suggests that these benefits are probably not going to be present. But even if they are, by the latter parts of the century, if temperatures get up above 5 degrees, from where they are at present, that all agricultural productivity will suffer as a result. So it's not clear that these benefits need to be built into the model and given as much prominence as they have. One of the things we wanted to do in our Economics of 350 report to really sort of drive home the message that assumptions drive the model, you change the assumptions, you get different results, right, was to take the famous DICE model, okay, by William Nordhaus, and change some of the key assumptions of that model to reflect what we think are more accurate characterizations of the science and better treatment of, you know, potential future harms. Change those assumptions and just see if we could get this model to recommend 350 as an optimal policy target. And we did this not because we think that we have to make the case for 350 on the basis of kind of this narrow cost-benefit framework. On the contrary, I'm going to argue that we shouldn't. But just to demonstrate to others the power of these assumptions, okay? So we called it rolling the dice for 350. What did we do? The first thing we did is we lowered that discount rate so that future benefits from avoided warming actually matter in present value terms, okay? We didn't just kind of willy-nilly pick a discount rate. We actually borrowed the discount rate that was used in the famous Stern review to the British government on climate change that came out in 2006, I believe. And for those of you who have been sort of, you know, studious followers of the climate debate, you'll know that when Nicholas Stern, who was the former chief economist at the World Bank, when he produced that report, it created quite a storm because it was the first really high-profile economist at that point to basically come out and say, wow, we really need to do something about climate change, the benefits of avoided warming outweigh any of the potential costs of the global economy in the short run. And how did he reach that conclusion? He reached it by changing the discount rate from the 6%, which had been commonly used up until then, down to only about 1.5%. And he's gotten a tremendous amount of flack for it from many economists as a result. But we borrowed his discount rate of 1.5%. So basically now we've said the future matters. We changed what's called the climate sensitivity parameter, basically what's showing us the long-term temperature increase from a doubling of CO2 emissions in the atmosphere. We're saying what Hansen's now warning, that a doubling of CO2 might lead to 6 degrees of warming, not just 3 degrees of warming. So we've updated the science. And the third thing we did is we changed the shape of the damage function. Basically this relationship between average temperature increase and the amount of economic damage that results because of that increased temperature. So we changed the damage function to basically capture the fact that we believe that the damages from climate change will be very economically significant, right? And we played around with different shapes of the damage function as well. And what we showed is that no matter what variation of the DICE model we worked with, if we assume that climate sensitivity is greater, that damages are greater, and that the future does in fact matter, then even the DICE model can recommend 350 parts per million as the optimal policy objective. So for those who believe that we have to argue climate policy on the grounds of these cost-benefit models, we can do it if we just bring in the right assumptions. Okay. Now, kind of taking a step back from modeling back into the real world, right? And answering the question, well, to get to 350, right, if we are going to agree that 350 is optimal, what is it actually going to take to get there? And we looked at two different scenarios. The one is the scenario that Hansen sort of outlines in his work, pushing for a 350 parts per million target. And his scenario for getting to 350 gets us there by 2100, okay? And he basically assumes that coal will either be completely phased out by 2030 or that we will have achieved 100% carbon capture and storage. Okay? He assumes that we can continue to use the oil and gas reserves that the IPCC has estimated are available, and that we will use less and less of these as, through market forces, oil and gas prices continue to rise steadily as these resources near their exhaustion points. He assumes, and this is a very important part of his scenario for getting to 350 by 2100, we need a combination of both ending deforestation and all the emissions that are produced by deforestation, as well as large-scale reforestation. All right, so growing forests on areas that were previously forest covered but have lost their forest, and other technologies that would be necessary to achieve negative emissions. Now, what do I mean by negative emissions? I mean taking more emissions out of the atmosphere each year than we're putting in. And as it turns out, negative net emissions is a critical assumption in Hansen's scenario for getting to 350 by 2100. Okay? It's hard to see how you can get to 350 by 2100 without negative net emissions. Okay. What we wanted to do is say, well, wait a minute, is there an alternative path to 350 that doesn't rely on negative net emissions and all of the technological changes that would have to take place between now and then for those negative net emissions to come online? And so we modeled what would it take to get to 350 by 2200, so 100 years later, which means that we're going to be above the 350 parts per million target for a longer period of time, and therefore this is a much riskier scenario than the one Hansen is recommending. Okay? And we say this not because we think this is the better scenario, right? Certainly if we can make it technologically possible to get 350 by 2100, we need to do it. But if we can't, if we can't bring negative net emissions online large scale, can we get there by 2200? And the answer is yes, we can. What's it going to look like? We're going to have to reduce emissions to 54% of 1990 levels by 2020. and then reduced to 3% by 2050. So essentially we're saying the world has to be free of new carbon emissions by 2050, 97% reduction, as compared to, say, the 80% by 2050 that people are talking about to get to the 450 parts per million target. Okay. This basically assumes that we have completed the conversion to renewable energy systems and that the world's virtually emissions-free by mid-century. And of course, this is a far more ambitious scenario than any of the current policy proposals under discussion. Okay? But this is what it will likely take to get there, okay, without negative net emissions. Okay? For those of you who like a picture better than words, the top line, this is cumulative emissions we're graphing, not atmospheric levels. The red line on the top demonstrates getting to 350 by 2200, so that was that alternative scenario that we put together. And then the blue line, of course, is Hansen's 350 by 2100, and the dipping down is the effect of those negative net emissions coming online. We're taking more out by about mid-century under Hansen's scenario than we're putting in. And that's how he gets us to 350 by the end of the century as compared to by 2200. Okay. Oops, excuse me. There we go. You know, whether we're talking about 350 by 2100 or 2200, right? Very ambitious proposals, large-scale changes that have to take place. And so the obvious question that gets asked is, can we afford it? Okay? And so what we did in this 350 report is we combed the academic literature, we combed the reports coming out of research institutes, we talked to individual researchers across the world who are looking at these subjects to try to find out what has anybody discovered with respect to the economics of a 350 target, okay? And not surprisingly, of course, what we found is there is a lag between what science and policy is beginning to talk about, 350 parts per million, and what's been published in the academic literature, right? And that's partly a function of, to publish anything in academia, it takes, you know, sometimes years for ideas to see the published light of day. And so given the relative newness of the recommendation for 350, there hasn't been that much work done. Most of the economics literature has addressed much higher stabilization targets of 450 or 550. However, there have been 4 major modeling initiatives by academic research groups, some of them in Europe, that have projected the cost of achieving a 350 parts per million target. So what did these studies find? Well, of the 4, one begins with an assumption that the global economy looks, strangely enough, just like it does now, with high unemployment, underutilized resources, okay? And with that starting assumption, right, what they find is that the initiatives and the efforts that would have to take place to get us to 350 would actually have a stimulating effect on the global economy. And that is that climate policy would create jobs and actually speed up economic growth if we started from a point in time that looks very much like where the global economy is at present, and certainly where the US economy is at present, okay? The other 3 groups basically assumed, which is a more de facto assumption in economics, that all resources, including labor resources, are currently being fully utilized, so there's no chronic unemployment problem. And starting from that assumption, right, what they found is that there would be that climate policy aimed at 350 would have no effect on employment in the long term, and that it would have costs, but the cost would fall somewhere in the range of only 1 to 3% of world output for many years into the future. Okay? So 1 to 3% of world output. Okay? The question then becomes, is that a big number or a small number? Is that a price we can pay and are willing to pay, or a price that essentially says game over? It really depends on your context, okay? Let's suppose that if we take this 1 to 3% range, let's grab 2.5% at the top end of that, okay? and suppose that climate protection is going to cost 2.5% of world output for many years. Is that too expensive? Well, too expensive compared to what? Compared to the cost of inaction? Compared to the cost if we do nothing? All right, and we let the climate continue to heat up and all of the changes that have been predicted to take place, right? Probably not, right? It is impossible to put a single dollar value on what climate change and all of its manifestations will look like, 100 years from now, right? But if we believe the science and we understand what the science is telling us in terms of the effects on agricultural systems, water supplies, human health, low-lying areas, including major cities, right? Then, species extinction. If we believe and understand the science, then it's hard to conclude anything other than there will be a large economic price tag associated with those changes or adaptation to those changes. Okay, so if we're going to compare 2.5% of world output to get to 350 parts per million with the cost of inaction, cost-benefit analysis, I think, is almost always going to tilt in favor of taking immediate action, right? The bad news that we keep hearing from climate scientists is not that is raising the cost of doing nothing about the climate problem. It's not raising the cost of doing something. The bad news out there isn't that we can't afford to solve the climate problem. The bad news is that the economic cost of not solving the climate problem are becoming almost incalculable. Okay. Now, to put it in kind of other context, in a good year, a typical good year, our economy here in the U.S. will grow at about 2.5% a year. Okay, and so we're talking about basically then spending 2.5%, right, of our economy on climate protection. Okay. What does that mean? It means we would basically skip 1 year's worth of economic growth in the U.S., and then we would resume. And as a result, we would forever have 2.5% less, every year thereafter, right? Because you never make up the 2.5% you lost, right? Well, skipping 1 year's growth in the U.S., how disastrous would that be, right? How different is the material standard of living for the average American from, say, 2006 to 2007? Not very different at all. Okay, so that's the magnitude of what we're talking about. Another way of thinking about it, household income in the United States, it would double in 29 years if we spent 2.5% of output today to solve the climate problem, rather than doubling in its projected 28 years. Okay, so can we wait another year for incomes in the United States to double? Probably. Okay, at least I believe so. Now, what about for developing countries? Okay, where obviously any sacrifice of current growth has a much higher opportunity cost, right? There's a much larger sacrifice involved. Well, if we take a look at China, for example, China, which is kind of cooking along at say, a 10% annual growth rate in a good year, for China to invest 2.5% of its output on preventing climate change would be equivalent to skipping just 3 months' worth of growth, because their economy is growing so quickly, before resuming. And it means that in China, household incomes would double in 86 months as compared to 83. Okay? So these are not huge changes in the standard of living for the average person. Okay? I think the only way that spending this sum of money, and let's make no doubt about it, when you're talking about 2.5% of the global economy, there are a lot of zeros there, right? I mean, we have a $60 trillion economy, right? The only way that it really starts to make sense to spend that sum of money on climate prevention is if we, one, accept the science, right, and believe what the science is telling us about what climate change can do to our social systems, our ecological systems, and our economic systems, okay? But also, we need a different framework for thinking about it. We need to go beyond just sort of this narrow weighing of, well, what are the benefits versus what are the costs, okay? Because even though we could probably demonstrate it that way, right, it's not altogether satisfactory, and it's not clear that that's the way we should be thinking about the climate problem. It's not the way that we necessarily think about other problems that are analogous to climate change, okay? For example, this problem, Okay, this is a house on fire. Okay. What do we do to protect ourselves against potential home fires, right? We buy insurance. We buy fire insurance. Now, as it turns out, in most cases, it's the bank who holds our mortgage that's requiring us to buy fire insurance. But ask how many people would, not purchase fire insurance even if the bank didn't require it, right? And you'd probably find a few who, are real risk takers who would not pay for fire insurance. Why is it that the bank makes us pay for fire insurance, right? It's not because they think your house is going to burn down, but because they can't be sure that it won't, right? And if your house burns down, right, the costs are really large. So we're talking about a scenario where there's a degree of uncertainty about a future event, but the consequences of that future event are potentially so disastrous that it warrants taking preventative measures in the present in the form of insurance. Okay. We do this a lot, actually. Okay. Again, one of my colleague looked up to see just how often do homes actually burn down here in the U.S. And the average annual number of residential fires in the U.S. is about 0.4% of the number of housing units. Okay, really small. The average home has a fire once every 250 years, which means the chances are good that your home will never burn down in the time that you're living in it. If we look at another common insurance scenario, healthy young couples who buy life insurance, even though they have no history of medical problems or no reason to believe that their death is imminent, right? They have even lower annual risks of death than a home fire at 0.1 to 0.2%, but many healthy young couples purchase life insurance, particularly if they have children, okay? You don't buy fire insurance because you're sure your house will burn down. You don't buy life insurance because you think your life is going to prematurely end and leave your children vulnerable. You buy it because you can't be sure that it won't, okay? And so if people accept this kind of rationale with respect to insuring themselves against other uncertain but potentially catastrophic risks, why wouldn't the same logic therefore apply to thinking about climate change? In which case, then, the reason we should be spending 1 to 3% of output on climate protection is that spending now on emissions reduction is really an insurance policy for future generations. We don't know for sure that climate change will occur the way scientists say that it very well might, and we can't know for sure that the effects will be catastrophic, although there's certainly good reason to believe that they will be. But what we do know is that by doing nothing and temperatures rise, the risks of catastrophic outcomes become more and more likely. And so we can think of spending now to avoid those worst-case future scenarios as an effective future policy for our children and our grandchildren. Okay. Well, that's really nice. Nice to think of it as an insurance policy, but can we actually do it? Can we really afford it? Okay. Can the U.S. economy spend 2.5% or anywhere in that 1 to 3% range of global output to force the emissions reductions we need to get to 350 parts per million? Can we do it? Can the world afford it? Well, we already do, okay, in other areas, okay? 68 countries around the world spend at least 2.5% of their GDP on military. Okay. The U.S. and China, kind of the world's largest two greenhouse gas emitters, have military spending that's over 4% of our gross domestic product. Okay. An interesting question to ask is, if we cut the military budget from 4% of GDP down to 1%, right? Would anybody really invade the U.S. or China? Would both countries be safer if we diverted 2/3 of their military budgets to climate protection? Right? And which has a greater immediate threat to one's family and one's household? Climate change or outside military threats? Okay. My point here is not to argue that the way we're going to solve the climate problem is we're going to slash the military budget, we're going to move all the money into climate protection. And I certainly don't want to get into a debate about whether that makes sense to do. My point is just to demonstrate that the magnitudes we're talking about are well within the range of the magnitudes of spending on other type programs, large programs, okay, designed in the interest of national security. Okay. Okay. So if we're going to spend this kind of money, well, what are we going to spend it on? Okay. Well, we're going to need both short-run and long-run plans. First and foremost, first thing we have to do, we have to adopt all of the available low-cost and no-cost emissions reduction opportunities identified by the McKinsey Institute and others. Okay? These are the studies that show very credibly, have been well vetted, that we could get up to maybe as much as a third of U.S. emissions reductions through energy efficiency and other technologies that already exist and have already been demonstrated to be cost effective. We just need to do wide-scale implementation. Okay? So certainly we have to do that. That one's sort of the no-brainer, right? That's the one that's just sitting there staring us in the face and we continue to ignore it. Okay? We're ignoring it as we're running around arguing over point 2, which is setting a carbon price, right? And that is absolutely critical for climate policy. We need a cap on carbon emissions. A cap will generate a carbon price. A carbon price is useful, but it alone won't get the job done either, right? And while I'm absolutely supportive of U.S. policy initiatives aimed at capping U.S. emissions and setting a very firm price signal for carbon, it is regrettable that so much attention has been focused on that these other two components, the adopting the energy efficiency and then the research and development into new technologies, has been relatively less explored. We need new technology, folks, okay? And we can't just rely on, technology to kind of come along in its own accord, okay? Government, in this case, is going to have to play a major role in funding and directing our research efforts, okay? That could be government working alongside and should be working alongside the private sector, but we need a major coordinated, directed research initiative. Okay. Okay. I wanted to throw this picture in here. The date on this picture is somewhere in the 1950s, I believe. This is what, the state of modern computing was at the time, right? Not that long ago. I wonder, looking at those, two men in the picture who are probably way advanced in their use of technology, certainly were way advanced compared to the average person, if they could have imagined the suite of technologies that are available and commonplace today. The laptop computers, the iPods, the cell phones, right? The whole suite of technologies that modern microelectronics has made possible, right? It probably would have been hard to imagine those possibilities at this point in time, just like it's hard for us today to imagine the possibilities which are going to be dominant 50 years from now, okay? But they will occur and can occur. In all of these scenarios, right, whether it's 450, 350, right, the pace of technological change is absolutely critical, okay? And so it bears reminding how it is that major technological changes and innovations have actually taken place over the course of history, okay? So we call this a recipe for a world-changing technological revolution. Or alternatively, how the Pentagon invented microelectronics. Because the truth is that, so much of the technology that we depend on today that defines the modern economy in the year 2010 were the byproducts of concerted, organized, coordinated, spending via the military for military-related technologies. Okay, that's where microelectronics came out of. Okay, that's where the internet came from. And how is it that we were able to kind of mobilize that kind of rapid and massive technological change? Well, the first thing we did was, during the Cold War, we detected a fundamental threat to our way of life, right? We posed it as a national security issue. We needed these technologies in order to protect U.S. national security, right? And it worked. Everybody was on board. Well, one could argue that climate change poses a fundamental threat to our way of life. We announced a massive mobilization to defeat the threat. Right? That was the Cold War. We then set impossible performance targets for new technologies. You know, land a missile on a dime, right? Don't know how we're going to do it, but we knew we needed to be able to do it. Okay? We knew where we had to go, we just weren't sure how to get there. We set these impossible performance targets, and we spent large amounts of money to meet those targets, right? And it attracted some of the best and the brightest minds, right, who were able to deliver. Okay? Right? We could do the same thing, we have to do the same thing again with respect to climate change. Okay. You can see I'm running out of time, so I'll just wrap up. In conclusion, what is it going to take to get to 350? First and foremost, technological change, right? And what we see is that negative carbon technologies, be they reforestation, biochar, or perhaps bioengineering, which is showing some promise, you know, the pace of those technologies will determine if and how fast we get to the 350 parts per million target, okay? Getting to 350 is also going to depend on avoided deforestation. Okay, we need to really ramp up our efforts, particularly in other parts of the world, to end the large-scale deforestation that's so devastating to the world's biodiversity, but is also contributing in a very significant way to the global climate problem. We need rapid and wide-scale adoption of energy efficiency improvements. We need public policy that's going to set a clear and consistent carbon price. And we need major coordinated spending on research. These are the ingredients for how we can get to 350. Okay. If we do that, economic studies have demonstrated that we can actually afford the cost of achieving a 350 parts per million target, which means that despite the, you know, sometimes popular opinion or popular sense that economics is what's standing in our way, solving the climate problem is most fundamentally a problem of political will, not economic or technical capacity and capability. And what we really can't afford is too little climate policy too late. Thank you.